The universe is vast, mysterious, and filled with secrets that defy our understanding. Did you know that 95% of everything that exists, dark matter and dark energy, remains completely invisible to us? We can't see it, touch it, or even fully comprehend it, yet it shapes the very fabric of reality. This is just one of the countless cosmic puzzles that leaves scientists scratching their heads. From the enigmatic behavior of black holes to the mind-bending nature of time itself, the universe is a treasure trove of unanswered questions. And today, we're diving into the top 20 mysteries that continue to baffle even the brightest minds. These aren't just scientific curiosities, they're the keys to understanding the very essence of existence. So, if you've ever looked up at the night sky and wondered what lies beyond the stars, you're about to embark on a journey into the unknown. Let's explore the greatest enigmas of the cosmos together. Imagine a substance so pervasive that it makes up over a quarter of everything in the universe, yet it's completely invisible. No telescope, no microscope, no instrument we've ever built can directly detect it. This is the mystery of dark matter. Despite its invisibility, we know it's there because of the way it bends the rules of gravity. Galaxies spin faster than they should, and galaxy clusters move in ways that defy the laws of physics as we understand them. The only explanation, an unseen force, a hidden mass pulling strings behind the scenes. Scientists call this dark matter, and it's one of the most profound puzzles in modern science. But what exactly is dark matter? The leading theory suggests it's made up of particles called WIMP, weakly interacting massive particles. These hypothetical particles don't interact with light or ordinary matter, which is why they are so elusive. Yet, despite decades of searching, we haven't found definitive proof of their existence. Experiments deep underground, shielded from cosmic interference, have tried to catch a glimpse of these ghostly particles, but so far, the results remain inconclusive. Could dark matter be something even stranger than WIMP? Some researchers speculate it might be an entirely new form of matter, one that operates outside the boundaries of our current physics. The implications are staggering. If dark matter is something beyond our current understanding, it could rewrite the rules of the universe itself. And while we grapple with this invisible enigma, there's another mysterious force at play, one that's even more elusive and powerful. But that's a story for the next mystery. For now, dark matter reminds us that the universe is far stranger than we can imagine, and the answers we seek might lie just beyond the edge of our perception. While dark matter pulls the universe together, there's another force at work, one that's doing the exact opposite. Picture this: the universe isn't just expanding, it's accelerating. Galaxies are racing away from each other faster and faster, as if some unseen hand is pushing them apart. This mysterious force is called dark energy, and it makes up a staggering 68% of the universe. Unlike dark matter, which tugs on galaxies with gravity, dark energy seems to be working against it, stretching the fabric of space itself. So, what exactly is dark energy? The simplest explanation comes from Einstein's cosmological constant, a term he originally added to his equations to describe a static universe. Though he later dismissed it as his greatest blunder, modern scientists have revived the idea to explain the accelerating expansion. According to this theory, dark energy is a property of space itself, a constant energy density that fills the cosmos and drives it apart, but not everyone is convinced. Some researchers propose alternative ideas, like quintessence, a dynamic field that changes over time, and could explain why the expansion rate isn't perfectly uniform. The challenge with dark energy is that it's even more elusive than dark matter. We can't see it, measure it directly, or even fully understand its nature. All we know is that it's there, shaping the fate of the universe on the grandest scale. If dark energy continues to dominate, the cosmos could end in a big freeze, where galaxies drift so far apart that the universe becomes a cold, empty void. On the other hand, if dark energy behaves differently than we think, it could lead to a big rip, tearing apart everything from galaxies to atoms. Studying dark energy is like trying to solve a puzzle with missing pieces. We're limited by the tools we have and the vastness of the universe itself. Yet, every observation brings us closer to understanding this enigmatic force. And while dark energy challenges our current understanding of physics, it also opens the door to new possibilities, perhaps even a completely new framework for how the universe works. But as we grapple with the mysteries of dark energy, another question looms even larger. How did the universe begin in the first place? That's a mystery that takes us back to the very beginning of everything. The Big Bang is often described as the moment everything began, a colossal explosion that birthed the universe as we know it. But here's the twist: the Big Bang wasn't an explosion in the traditional sense. Instead, it was the rapid expansion of space itself, a sudden stretching of the cosmos from an unimaginably hot and dense state. This theory, supported by overwhelming evidence like the cosmic microwave background radiation, has become the cornerstone of modern cosmology. Yet for all its explanatory power, the Big Bang leaves us with more questions than answers. What caused the Big Bang? What, if anything, existed before it? These are the kinds of questions that keep cosmologists up at night. The Big Bang theory describes the universe's evolution from a fraction of a second after its birth, but it doesn't explain what triggered it. Some scientists speculate that the Big Bang might have been the result of a quantum fluctuation, a random event in a pre-existing void. Others suggest it could have been the collision of higher dimensional objects in a multiverse. But these ideas are still speculative, and we lack the tools to test them directly. Adding to the mystery is the concept of cosmic inflation. In the first moments after the Big Bang, the universe is thought to have undergone an exponential expansion, growing trillions of times in size in less than a blink of an eye. This idea helps explain why the universe appears so uniform on large scales, but it also raises new questions. What drove this rapid expansion, and could it have happened more than once, leading to multiple universes? The multiverse theory suggests that our universe might be just one of countless others, each with its own set of physical laws. It's a mind-bending idea, but one that's difficult to prove with our current technology. Speaking of technology, that's another hurdle in our quest to understand the Big Bang. The earliest moments of the universe are shrouded in a veil of extreme energy and density, far beyond what our most powerful particle accelerators can recreate. Even the cosmic microwave background, our best window into the early universe, only takes us back to about 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely, leaving us with a cosmic blind spot. Despite these challenges, the Big Bang remains one of the most profound discoveries in science, offering a glimpse into the origins of everything. But as we piece together the story of the universe's birth, another mystery emerges, one that's equally puzzling. Why does the universe seem so perfectly fine-tuned for life? From the strength of gravity to the mass of subatomic particles, the constants of nature appear to be precisely calibrated to allow stars, planets, and ultimately us to exist. This fine-tuning is so precise that it's hard to chalk it up to mere chance. So, what's the explanation? That's a question that takes us into the heart of one of the universe's greatest enigmas. The universe is a delicate balancing act, and the more we study it, the more we realize just how finely tuned it is for life. Take gravity, for example. If it were even slightly stronger, stars would burn out too quickly, leaving no time for planets to form. If it were weaker, stars might never ignite at all. The same goes for the other fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Each one is precisely calibrated to allow atoms, molecules, and eventually life to exist. This remarkable precision is what scientists call the fine-tuning problem, and it's one of the most perplexing mysteries in cosmology. So why is the universe so perfectly suited for life? One possible explanation is the Anthropic Principle, which suggests that the universe must be compatible with the existence of observers, us, because we're here to observe it. In other words, if the constants of nature weren't just right, we wouldn't be around to wonder why. But while this idea offers a philosophical answer, it doesn't explain why the universe is fine-tuned in the first place. Is it pure luck, or is there something deeper at play? Some scientists argue that fine-tuning points to the existence of a multiverse, a vast collection of universes, each with its own set of physical laws. In this scenario, our universe is just one of countless others, and it's no surprise that we find ourselves in the one where the conditions are right for life. The multiverse theory is intriguing, but it's also controversial. After all, if we can't observe or interact with these other universes, how can we ever prove they exist? It's a tantalizing idea, but one that remains firmly in the realm of speculation. Others take a different approach, suggesting that fine-tuning might be evidence of a deeper design, a cosmic blueprint that ensures the universe evolves in a way that allows life to flourish. This idea often leads to discussions about the role of a creator or some form of intelligent agency, though it's important to note that science doesn't currently have the tools to explore such questions. The fine-tuning problem, then, remains an open question, one that challenges our understanding of the universe and our place within it. What's fascinating is how this mystery connects to the very fabric of reality. The constants of nature aren't just arbitrary numbers, they're the foundation of everything we see and experience. And while we may not yet have the answers, the search for them pushes the boundaries of science and philosophy alike. As we ponder the fine-tuning of the universe, another question arises, one that's equally profound and equally mysterious. What is time, and why does it flow in only one direction? That's a puzzle that takes us into the heart of one of the universe's most enigmatic phenomena. Time is one of those things we all experience, yet it remains one of the most baffling concepts in science. Why does it always move forward? Why can't we rewind it like a video? This is the mystery of the arrow of time, and it's deeply tied to a concept called entropy. Entropy is essentially a measure of disorder in the universe, and according to the second law of thermodynamics, it always increases over time. Think of it like this: if you drop a glass and it shatters, the pieces don't spontaneously reassemble themselves. That's entropy at work, and it's why time seems to flow in one direction from order to chaos. But here's where things get weird. While entropy explains why time moves forward on a macroscopic scale, it doesn't quite fit with the rules of quantum mechanics, which govern the behavior of particles at the smallest scales. In the quantum world, time doesn't seem to have a preferred direction. Particles can move backward and forward in time without breaking any rules. So how do we reconcile these two seemingly contradictory views of time? That's a question that has puzzled physicists for decades. One intriguing idea is the block universe theory, which suggests that past, present, and future all exist simultaneously. In this view, time is like a giant block of space-time, and our experience of moving through it is just an illusion. It's a radical idea, but it helps explain why the laws of physics don't seem to care about the direction of time. If the block universe theory is correct, then the flow of time we experience might just be a byproduct of how our brains process information. And then there's the tantalizing possibility of time travel. Could we ever build a machine that lets us jump backward or forward in time? Theoretically, yes, but it would require bending the fabric of space-time in ways we can't yet imagine. Wormholes, hypothetical tunnels through space-time, are often proposed as potential time machines, but they come with their own set of challenges. For one, they'd require exotic matter with negative energy to stay open, and we have no idea if such matter even exists. Even if it does, the energy required to create a stable wormhole would be astronomical. The nature of time is a puzzle that touches on everything from the smallest particles to the largest structures in the universe. It's a reminder that even the most familiar aspects of reality can hide profound mysteries. And as we grapple with the enigma of time, another cosmic puzzle looms on the horizon, one that's just as mysterious and even more extreme. What happens when gravity becomes so strong that not even light can escape? That's the question that takes us into the heart of black holes. Black holes are the universe's ultimate enigmas, regions of space where gravity is so intense that nothing, not even light, can escape. Imagine a place where the rules of physics as we know them break down, where time and space twist into something unrecognizable. At the heart of every black hole lies a singularity, a point of infinite density where the laws of physics simply stop working. Surrounding this singularity is the event horizon, the point of no return. Once something crosses this boundary, it's gone forever, swallowed by the black hole's immense gravitational pull. But black holes aren't just cosmic vacuum cleaners. They're also laboratories for testing the limits of our understanding. Take the information paradox, for example. According to quantum mechanics, information about the state of a particle can never be destroyed. But if something falls into a black hole, it seems to vanish completely, taking its information with it. This contradiction has puzzled physicists for decades, and it's still far from being resolved. Stephen Hawking proposed a partial solution with his theory of Hawking radiation, which suggests that black holes aren't entirely black. Instead, they emit tiny amounts of radiation over time, slowly losing mass and eventually evaporating. But even this theory doesn't fully explain what happens to the information trapped inside. Recent breakthroughs have brought us closer to understanding these cosmic giants. In 2019, the Event Horizon Telescope captured the first ever image of a black hole, revealing a glowing ring of light around the event horizon. This groundbreaking achievement confirmed many predictions about black hole behavior, but it also raised new questions. For instance, why does the ring of light appear so uniform? And what exactly is happening at the singularity? These are questions that even the most advanced telescopes can't answer yet. Black holes challenge our understanding of space, time, and reality itself. They're places where the familiar rules of the universe no longer apply, and where the deepest mysteries of physics come to the surface. But as we push the boundaries of our knowledge, another tantalizing possibility emerges, one that could connect distant parts of the universe in ways we can barely imagine. What if black holes aren't just cosmic dead ends, but gateways to something even more extraordinary? That's where wormholes come into the picture. Wormholes are one of the most fascinating ideas in theoretical physics, a cosmic shortcut through the fabric of spacetime itself. Picture the universe as a vast sheet of paper. If you wanted to travel from one side to the other, the longest route would be to move across the surface. But what if you could fold the paper, bringing two distant points together and punching a hole through them? That's essentially what a wormhole would do. Create a tunnel connecting two far-flung regions of space or even different points in time. It's a concept straight out of science fiction, but it's rooted in the equations of Einstein's theory of general relativity. The idea of wormholes opens up mind-bending possibilities. Imagine being able to travel across the galaxy in an instant or even journeying back in time. Theoretically, a wormhole could serve as a bridge between 2 points in spacetime, allowing for faster-than-light travel without breaking the cosmic speed limit. But here's the catch: wormholes, if they exist, would be incredibly unstable. The moment one formed, it would likely collapse in on itself almost instantly. To keep a wormhole open, you'd need something called exotic matter, a hypothetical substance with negative energy that could counteract the immense gravitational forces trying to crush it. The problem: we have no evidence that exotic matter exists, and creating it would require technology far beyond our current capabilities. Even if we could stabilize a wormhole, there's another hurdle: we've never actually observed one. Wormholes remain purely theoretical, a product of mathematical equations rather than direct evidence. Some scientists speculate that tiny wormholes might have formed in the early universe, but they'd be far too small for anything to pass through. Others suggest that wormholes could be hiding in the hearts of black holes, but exploring that idea would require venturing into regions of spacetime where our understanding of physics breaks down completely. Despite the challenges, the concept of wormholes continues to captivate scientists and dreamers alike. They represent a tantalizing possibility, a way to transcend the limits of space and time, to explore the universe in ways we can barely imagine. But as we ponder the potential of wormholes, another question arises, one that's equally profound and far more immediate. If the universe is so vast and the conditions for life are so finely tuned, where is everyone? This is the essence of the Fermi Paradox, a mystery that challenges our understanding of life in the cosmos. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Given the sheer scale of it all, you'd think we'd have stumbled upon some sign of intelligent life by now. But so far, the cosmos has been eerily silent. This is the essence of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" If the conditions for life are so finely tuned and the universe is so expansive, why haven't we encountered any evidence of extraterrestrial civilizations? It's a question that has puzzled scientists and dreamers alike for decades. One possible explanation is the Great Filter theory. The idea is that somewhere along the path from simple life to advanced civilizations, there's a barrier, a filter, that's incredibly difficult to overcome. This filter could be behind us, meaning that the emergence of intelligent life is so rare that we're one of the few, if not the only, species to have made it this far. Or more unsettlingly, the filter could lie ahead of us. Perhaps advanced civilizations inevitably destroy themselves through war, environmental collapse, or some other catastrophic event. If that's the case, humanity's future could be far more precarious than we realize. Another possibility is that intelligent life is simply too rare. Even in a universe teeming with planets, the conditions necessary for complex life might be so specific that civilizations like ours are exceedingly uncommon. Or perhaps intelligent life is common, but it's fleeting. Civilizations might rise, flourish, and then disappear before they have a chance to make contact with others. This idea ties into the concept of the silent universe, where advanced societies might exist, but they've chosen to remain hidden, either out of caution or because they've evolved beyond the need for outward communication. Then there's the possibility that we're just not looking in the right way. Our current methods of searching for extraterrestrial life, like scanning for radio signals, might be outdated. Advanced civilizations could be using technologies we can't even imagine, making them invisible to our current tools. Or perhaps they're communicating in ways we don't yet understand, using methods that are completely alien to us. The universe is full of mysteries, and our search for life is still in its infancy. The Fermi Paradox isn't just a scientific curiosity, it's a profound question about our place in the cosmos. If we're truly alone, it underscores the fragility and uniqueness of life on Earth. If we're not, it raises questions about why we haven't made contact and what that might mean for our future. Either way, the search for answers pushes us to explore, to innovate, and to dream. And as we ponder the silence of the universe, another cosmic mystery beckons, one that's pulling entire galaxies toward it with an irresistible force. What is the Great Attractor, and why is it tugging on our corner of the cosmos? That's a question that takes us deeper into the hidden forces shaping the universe. Hidden in the depths of the cosmos lies a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at astonishing speeds. This mysterious gravitational anomaly is known as the Great Attractor, and it's one of the most perplexing enigmas in modern astronomy. Located roughly 250 million light-years away, the Great Attractor exerts an irresistible pull on everything in its vicinity, shaping the motion of galaxies on a colossal scale. But here's the catch, we can't see it directly. Its location lies behind the plane of the Milky Way, obscured by a thick veil of stars, gas, and dust. This cosmic blind spot makes studying the Great Attractor an immense challenge, leaving scientists to piece together clues from what little they can observe. So, what exactly is the Great Attractor? One leading theory suggests it's a massive cluster of galaxies, a dense region of space where gravity is amplified by the sheer concentration of matter. This idea aligns with what we know about galaxy clusters, which can exert significant gravitational influence over vast distances. But there's a twist. The Great Attractor's pull is even stronger than what a typical cluster should produce. This has led some researchers to propose that it might be something far more exotic, perhaps a supercluster of galaxies, or even a concentration of dark matter so immense that it warps the fabric of spacetime itself. Adding to the intrigue is the Shapley supercluster, a colossal structure located even farther away than the Great Attractor. Some scientists believe that the Shapley supercluster might be amplifying the Great Attractor's gravitational pull, creating a cosmic tug of war that's shaping the motion of galaxies across millions of light years. But without a clear view of the Great Attractor itself, these ideas remain speculative. The only way to unravel this mystery is to peer through the Milky Way's obscuring plane, using advanced instruments that can detect wavelengths of light unaffected by interstellar dust. The Great Attractor reminds us that even in an age of advanced technology, the universe still holds secrets just out of reach. It's a humbling reminder of how much we have yet to discover and how the cosmos continues to surprise us at every turn. But as we grapple with the mysteries of gravity on a galactic scale, another enigma awaits, one that operates on the smallest scales imaginable. What happens when two particles become so deeply connected that they defy the very nature of space and time? That's the strange and fascinating world of quantum entanglement. Quantum entanglement is one of the strangest and most fascinating phenomena in the universe, a concept so bizarre that even Albert Einstein called it spooky action at a distance. Imagine two particles separated by billions of light years, yet somehow still connected in such a way that the state of one instantly influences the state of the other. It's as if they're sharing a secret language that transcends space and time, defying everything we know about classical physics. This isn't science fiction. It's a real, experimentally verified phenomenon that lies at the heart of quantum mechanics. So how does quantum entanglement work? Let's break it down. When two particles become entangled, their properties like spin, position, or momentum are linked no matter how far apart they are. If you measure one particle and find it spinning clockwise, the other will instantly spin counterclockwise, even if it's on the other side of the galaxy. This instantaneous connection seems to violate the speed of light, which Einstein's theory of relativity says is the universe's ultimate speed limit. That's why Einstein was so skeptical, calling it spooky. But decades of experiments have confirmed that entanglement is real, and it's reshaping our understanding of reality. The implications are profound. Quantum entanglement suggests that the universe is far more interconnected than we ever imagined. It challenges the very idea of locality, the notion that objects are only influenced by their immediate surroundings. Instead, entanglement hints at a deeper layer of reality, where space and time might not be as fundamental as we think. This has led some scientists to propose that the universe could be fundamentally non-local, with particles sharing hidden connections that transcend the limits of spacetime. But entanglement isn't just a theoretical curiosity. It's also the foundation of emerging technologies like quantum computing and quantum communication. In a quantum computer, entangled particles can process information in ways that classical computers can't, solving complex problems in seconds that would take traditional machines millennia. Quantum communication, on the other hand, uses entanglement to create ultra-secure networks where information can't be intercepted or hacked without being detected. These technologies are still in their infancy, but they hold the potential to revolutionize everything from medicine to cryptography. Ongoing experiments continue to push the boundaries of what we know about entanglement. Researchers are testing its limits over increasingly vast distances, probing its role in the early universe, and even exploring whether it could be used to create a quantum internet. Each discovery brings us closer to unlocking the full potential of this mysterious phenomenon, but it also raises new questions. How far can entanglement stretch? Could it connect entire galaxies? And what does it mean for our understanding of the universe? As we delve deeper into the quantum realm, another mind-bending idea emerges, one that suggests the universe itself might be a kind of hologram. This is the holographic principle, a theory that proposes all the information in the cosmos could be encoded on a two-dimensional surface, like a cosmic projection. It's a radical idea, but one that could help explain some of the deepest mysteries of the universe, and that's where our journey takes us next. What if everything we see, touch, and experience, the stars, the planets, even you and me, is nothing more than a projection? This is the essence of the holographic principle, one of the most mind-bending ideas in modern physics. The theory suggests that the entire universe, with all its three-dimensional complexity, might actually be encoded on a two-dimensional surface like a cosmic hologram. It's a concept that sounds straight out of science fiction, but it has deep roots in some of the most advanced areas of science, including black hole physics and string theory. The idea first emerged from the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the amount of information a black hole can contain is proportional to its surface area, not its volume. This was a radical departure from classical physics, where information is typically tied to volume. Later, Stephen Hawking showed that black holes emit radiation and can eventually evaporate, raising questions about what happens to the information they've swallowed. The holographic principle was proposed as a solution. Perhaps the information isn't lost but is instead encoded on the black hole's event horizon, its two-dimensional boundary. From there, the idea expanded to suggest that the entire universe might work the same way, a vast, intricate hologram where all the information about reality is stored on a two-dimensional surface. String theory, a framework that attempts to unify all the forces of nature, also lends support to the holographic principle. In string theory, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, and the holographic principle offers a way to connect these higher dimensions to the three-dimensional world we experience. It's as if the universe is a projection of a deeper, more complex reality, one that we're only beginning to glimpse. But how could we ever test such a far-out idea? That's one of the biggest challenges. The holographic principle operates on scales so small and energies so high that our current technology can't directly probe it. However, scientists are looking for indirect evidence. For example, some researchers are studying the cosmic microwave background radiation, the afterglow of the Big Bang, for subtle patterns that might hint at a holographic universe. Others are exploring the behavior of particles in high-energy experiments, searching for clues that space itself might have a pixelated holographic structure. The implications of the holographic principle are staggering. If true, it would mean that our perception of reality is just a shadow of something far more profound. It could revolutionize our understanding of space, time, and the very nature of existence. But as we grapple with this radical idea, another cosmic mystery beckons, one that's etched into the oldest light in the universe. Why does the cosmic microwave background, the echo of the Big Bang, contain strange anomalies that defy our expectations? That's a question that takes us back to the very beginning of everything. The cosmic microwave background, or CMB, is often called the oldest light in the universe. It's the faint afterglow of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old. For decades, the CMB has been a cornerstone of cosmology, providing a wealth of information about the universe's origins and evolution. But as we've studied it more closely, we've discovered something unexpected: strange anomalies that don't fit neatly into our current understanding of the cosmos. These irregularities are like cosmic fingerprints, hinting at mysteries we're only beginning to unravel. One of the most puzzling features of the CMB is the so-called cold spot. This is a region of the sky where the temperature of the background radiation is significantly lower than the surrounding areas. At first glance, it might not seem like a big deal. After all, the universe is full of variations. But the cold spot is far larger and colder than what the standard model of cosmology predicts. It's as if there's a giant, unexplained void in the fabric of the universe, and scientists are still trying to figure out what could have caused it. Some researchers suggest that the cold spot might be evidence of a collision with another universe. This idea stems from the multiverse theory, which proposes that our universe is just one of many, each with its own set of physical laws. If another universe bumped into ours during the early moments of the Big Bang, it could have left behind a kind of cosmic bruise, a cold spot in the CMB. It's a wild idea, but one that's hard to prove without more evidence. Other explanations include exotic physics, like the presence of a supervoid, a vast, underdense region of space that could distort the CMB in unexpected ways. But even these theories struggle to fully account for the cold spot size and temperature. The cold spot isn't the only anomaly in the CMB. There are also strange patterns in the distribution of temperature fluctuations, as well as unexpected alignments in the polarization of the light. These irregularities challenge the assumption that the early universe was uniform and isotropic, the same in all directions. Instead, they suggest that there might have been something unusual happening during the universe's infancy, something that left its mark on the CMB. Could it be evidence of new physics or even a glimpse of a deeper layer of reality? The answers remain elusive, but the questions they raise are profound. As we continue to study the CMB, we're reminded that even our most well-tested theories have gaps. The standard model of cosmology has been incredibly successful, but anomalies like the cold spot show that there's still much we don't understand. They're a call to explore further, to push the boundaries of our knowledge and uncover the secrets hidden in the universe's oldest light. And as we ponder these cosmic riddles, another mystery comes into focus, one that's closer to home but no less perplexing. Where is all the ordinary matter in the universe? This is the missing baryon problem, and it's a puzzle that's been baffling scientists for decades. The universe is full of surprises, and one of the most baffling is the fact that we can't seem to find half of the ordinary matter that should be out there. This is the missing baryon problem, and it's a mystery that's been puzzling scientists for decades. Baryons are the building blocks of the visible universe: protons, neutrons, and the atoms they form. They make up everything from stars and planets to you and me. But when astronomers tally up all the baryons they can see, they come up short. About half of them are missing, and no one knows exactly where they've gone. So, where could all this matter be hiding? One leading theory points to something called the warm-hot intergalactic medium, or WIM. This is a vast, diffuse web of gas that stretches between galaxies, filling the voids of the cosmic web. The WIM is incredibly hot, millions of degrees, but also incredibly thin, making it nearly invisible to most telescopes. Detecting it requires looking for faint traces of highly ionized oxygen and other elements that absorb light from distant quasars. It's like trying to find a whisper in a hurricane, but recent observations have started to reveal hints of this elusive material. If the WIM exists, it could account for a significant portion of the missing baryons, solving one of the biggest puzzles in cosmology. But the WIM isn't the only possibility. Some scientists suggest that the missing matter might be hiding in other forms, like faint dwarf galaxies or even exotic particles that interact so weakly with light that they're nearly impossible to detect. Others propose that the missing baryons could be tied up in massive filaments of gas that haven't yet been observed. These filaments, if they exist, would act like cosmic highways connecting galaxies and shaping the large-scale structure of the universe. The challenge is that these structures are so faint and diffuse that they're incredibly difficult to spot, even with our most advanced instruments. Solving the missing baryon problem isn't just about filling in a gap in our cosmic inventory. It's about understanding how the universe works on the grandest scale. Baryons are the raw material for stars, galaxies, and planets, and their distribution tells us how the cosmos evolved over billions of years. If we can find the missing baryons, we'll gain a clearer picture of the universe's history and structure. But as we piece together this cosmic puzzle, another question looms, even larger one that's closer to home but no less profound. How did life emerge from the chaos of the early universe? That's a mystery that takes us to the very heart of existence itself. The origin of life is one of the most profound questions we can ask. How did something as complex and delicate as life emerge from the chaos of the early universe? It's a mystery that spans billions of years, from the formation of the first molecules to the intricate dance of DNA. And while we've made incredible strides in understanding the building blocks of life, the exact moment when chemistry gave way to biology remains shrouded in uncertainty. So, what do we know, and what are the biggest gaps in our understanding? One of the most intriguing theories is panspermia, the idea that life didn't originate on Earth at all, but was instead delivered here from elsewhere in the cosmos. Imagine a comet or asteroid carrying the seeds of life, microorganisms or organic molecules crashing into our planet billions of years ago. It's a compelling idea, especially given the discovery of amino acids, the building blocks of proteins, on meteorites. Panspermia suggests that life might be more widespread in the universe than we think, hitching rides on cosmic debris to spread across galaxies. But while it's an exciting possibility, it doesn't fully answer the question of how life began. It just shifts the mystery to another location. Closer to home, scientists have turned their attention to hydrothermal vents, the underwater geysers that spew superheated water rich in minerals. These vents, found deep in the ocean, are teeming with life today, and they might have been the cradle of life billions of years ago. The theory goes that the chemical-rich environment around these vents provided the perfect conditions for simple molecules to assemble into more complex ones, eventually leading to the first living cells. Experiments have shown that hydrothermal vents can produce organic compounds, but the leap from chemistry to biology is still a massive one. How did those molecules organize themselves into something capable of growth, reproduction, and evolution? That's the million-dollar question. Another key player in the origin of life is RNA, or ribonucleic acid. RNA is often seen as a precursor to DNA, capable of both storing genetic information and catalyzing chemical reactions. Some scientists believe that an RNA world existed before DNA-based life, where RNA molecules replicated themselves and laid the groundwork for more complex organisms. This idea has gained traction because RNA is simpler than DNA and can perform multiple roles, making it a plausible candidate for the first self-replicating molecule. But while RNA is versatile, it's also fragile, and the conditions needed for it to form spontaneously are still poorly understood. Recreating the conditions of early Earth is one of the biggest challenges in studying the origin of life. Our planet was a very different place 4 billion years ago, a chaotic volcanic world bombarded by asteroids and bathed in ultraviolet radiation. Simulating these conditions in a lab is incredibly difficult, and even when scientists succeed, the results are often ambiguous. Did life emerge in a warm little pond, as Charles Darwin once speculated, or in the depths of the ocean? Was it a gradual process, or did it happen in a sudden, dramatic event? These are questions that continue to drive research and debate. The search for life's origins isn't just about understanding our past, it's also about our future. If we can figure out how life began on Earth, we might have a better chance of finding it elsewhere in the universe. Are the building blocks of life common throughout the cosmos, or was Earth uniquely suited to spark the flame of biology? The answers could reshape our understanding of our place in the universe. But as we ponder the origins of life, another mystery emerges, one that's even more elusive and deeply personal. What is consciousness, and how does it arise from the physical matter of the brain? That's a question that takes us into the heart of what it means to be alive. Consciousness is perhaps the most intimate and baffling mystery of all. It's the experience of being you, the thoughts, feelings, and sensations that make up your inner world. But how does something as intangible as consciousness arise from the physical matter of the brain? This is what philosopher David Chalmers famously called the hard problem of consciousness, and it's a question that science has yet to answer. We can map brain activity, study neurons, and even simulate parts of the brain, but we still don't know how these processes give rise to subjective experience. Why does it feel like something to be alive? That's the puzzle at the heart of consciousness. One intriguing theory is panpsychism, the idea that consciousness is a fundamental property of the universe like mass or charge. In this view, even the smallest particles might have a tiny spark of awareness, and complex systems like brains simply amplify this basic property into the rich experiences we know. It's a radical idea, but it offers a way to bridge the gap between the physical and the mental. If panpsychism is true, then consciousness isn't something that emerges from matter. It's woven into the fabric of reality itself. But how could we ever test such a theory? That's where things get tricky, as consciousness is inherently subjective and difficult to measure. Another approach is integrated information theory, or EIT, which suggests that consciousness arises from the way information is processed and integrated in a system. According to EIT, any system with a high degree of interconnectedness, whether it's a brain or a computer, could, in theory, have some level of consciousness. This idea has sparked debates about artificial intelligence. Could a sufficiently advanced AI become conscious? And if so, how would we know? These questions aren't just philosophical, they have real-world implications for how we design and interact with technology. The mystery of consciousness also raises profound questions about life and the universe. If consciousness is a fundamental aspect of reality, does that mean the universe itself is, in some sense, aware? Could there be a cosmic consciousness, a kind of universal mind? These ideas might sound like science fiction, but they're taken seriously by some scientists and philosophers. And while we may not have the answers yet, the search for them is pushing the boundaries of what we know about the mind, the brain, and the nature of existence itself. As we grapple with the enigma of consciousness, another cosmic puzzle beckons, one that's far more tangible but no less mysterious. In the late 20th century, scientists noticed something strange happening to two spacecraft, the Pioneer 10 and Pioneer 11 probes. As they journeyed through the outer reaches of the solar system, they began to slow down in a way that couldn't be explained by gravity alone. This unexpected deceleration became known as the Pioneer Anomaly, and it's a mystery that's puzzled scientists for decades. What could be causing these spacecraft to drift off course? That's a question that takes us into the realm of the unknown, where even the laws of physics might not be what they seem. The Pioneer Anomaly is one of those cosmic puzzles that reminds us just how much we still have to learn about the universe, even within our own solar system. In the late 20th century, as the Pioneer 10 and Pioneer 11 spacecraft ventured beyond the orbits of the planets, scientists noticed something strange. The probes, which were expected to continue their journeys at a steady speed, began to slow down ever so slightly. This tiny deceleration, just a fraction of a millimeter per second squared, was far too small to be caused by gravity alone. It was as if some unseen force was gently tugging on the spacecraft, pulling them off course. This unexpected behavior became known as the Pioneer Anomaly, and it's a mystery that's puzzled scientists for decades. So, what could be causing this strange deceleration? one of the leading explanations points to thermal radiation. The Pioneer probes are powered by radioisotope thermoelectric generators which produce heat as a byproduct. Over time, this heat could have radiated unevenly from the spacecraft, creating a tiny but measurable thrust in the opposite direction. Think of it like a balloon releasing air. The escaping gas pushes the balloon forward. In the case of the Pioneers, the escaping heat might have acted like a faint cosmic breeze, slowing them down. This theory gained traction after detailed computer models suggested that thermal radiation could account for at least part of the anomaly. But while it's a plausible explanation, it doesn't fully solve the mystery. Some scientists argue that the thermal effects wouldn't be strong enough to explain the entire deceleration, leaving room for other possibilities. And that's where things get even more intriguing. Could the Pioneer anomaly be evidence of new physics? Some researchers have speculated that the deceleration might hint at a flaw in our understanding of gravity. Einstein's theory of general relativity has been incredibly successful at explaining the behavior of massive objects, but it's not perfect. On very small scales, like those inside atoms, or in extreme environments like near black holes, the theory starts to break down. Could the Pioneer anomaly be a sign that gravity behaves differently in the vast, empty reaches of space? It's a tantalizing idea, but one that's hard to prove without more data. Other theories suggest that dark matter or even exotic particles could be influencing the spacecraft, though these ideas remain speculative. The Pioneer anomaly also highlights the importance of precision in space exploration. Detecting such a tiny deceleration required incredibly accurate measurements, a testament to the ingenuity of the scientists and engineers who designed the mission. Even the smallest discrepancies can lead to groundbreaking discoveries, and the Pioneers are a perfect example of how meticulous observation can reveal hidden truths about the universe. But as we continue to explore the cosmos, we're reminded that not every mystery has an easy answer. Sometimes the universe throws us a curveball, challenging us to rethink what we know. And speaking of cosmic curveballs, there's another mystery that's just as puzzling and even more enigmatic. In 1977, a radio telescope in Ohio picked up a signal so unusual that the astronomer who discovered it circled it on the printout and wrote, "Wow." In the margin, this brief, powerful burst of radio waves has never been explained, and it remains one of the most tantalizing hints that we might not be alone in the universe. But that's a story for the next mystery. For now, the Pioneer anomaly reminds us that even in the familiar confines of our solar system, the universe is full of surprises. In 1977, a radio telescope in Ohio picked up something extraordinary, a signal so unusual that the astronomer who discovered it circled it on the printout and wrote, "Wow." In the margin, this brief burst of radio waves, lasting just 72 seconds, has since become one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Known as the WOW signal, it came from the direction of the constellation Sagittarius and matched the expected characteristics of a signal from an intelligent source. But despite decades of searching, the signal has never been detected again, leaving scientists to wonder, was it a fleeting message from an alien civilization or just a cosmic coincidence? The WOW signal stands out because it was incredibly strong, 30 times louder than the background noise, and it matched the specific frequency that scientists had identified as a potential marker for extraterrestrial communication. This frequency, known as the hydrogen line, is significant because hydrogen is the most abundant element in the universe. If an advanced civilization wanted to send a signal across the cosmos, this would be a logical choice. But here's the catch: no natural phenomenon we know of can produce a signal like this. It's as if the universe whispered something profound, only to fall silent immediately after. Over the years, numerous theories have been proposed to explain the WOW signal. Some suggest it could have been caused by a passing comet, reflecting radio waves from the sun. Others point to the possibility of a glitch in the telescope's equipment or interference from a human-made satellite, but none of these explanations fully account for the signal's unique characteristics. The most tantalizing possibility, of course, is that it was a deliberate transmission from an alien civilization. If true, it would be the first concrete evidence that we're not alone in the universe. But without a repeat signal, we're left with more questions than answers. The search for extraterrestrial intelligence, or SETI, has come a long way since 1977. Today, advanced telescopes and algorithms scan the skies for signals that might hint at intelligent life. Projects like Breakthrough Listen are analyzing millions of radio frequencies, searching for patterns that could indicate a message from the stars. But the challenge is immense. The universe is vast, and the odds of detecting a signal, let alone understanding it, are incredibly slim. Even if we do find something, verifying its origin would require more than just a single burst of radio waves. It would need to be consistent, repeatable, and unmistakably artificial. The WOW signal reminds us that the search for extraterrestrial life is as much about patience as it is about technology. It's a reminder that the universe is full of surprises, and that even the most fleeting moments can spark decades of curiosity. But as we continue to scan the skies for signs of intelligence, another cosmic mystery looms, one that's etched into the very fabric of the universe itself. Why does the cosmic microwave background, the afterglow of the Big Bang, contain strange patterns that seem to defy the laws of physics? This is the mystery of the axis of evil, and it's a puzzle that challenges our understanding of the cosmos on the grandest scale. When we look at the cosmic microwave background, or CMB, we're essentially peering back in time to the universe's infancy. This faint glow, the afterglow of the Big Bang, is one of our most powerful tools for understanding the cosmos. But hidden within this ancient light is a peculiar pattern that has left scientists scratching their heads. Known as the axis of evil, this anomaly refers to an unexpected alignment in the CMB's temperature fluctuations, a pattern that seems to line up with the plane of our solar system. It's as if the universe is subtly pointing a finger at us, and no one knows why. The name axis of evil might sound dramatic, but it's fitting for a mystery that challenges some of the most fundamental assumptions in cosmology. According to the Standard Model, the early universe should have been uniform and isotropic, meaning it should look the same in all directions. But the CMB's temperature fluctuations aren't entirely random. Instead, they appear to have a preferred direction, one that aligns eerily with the plane of our solar system. This alignment is so unlikely that it's been called a cosmic coincidence by some and a crisis for cosmology by others. Either way, it's a puzzle that demands an explanation. So, what could be causing this strange alignment? One possibility is that it's simply a statistical fluke, a quirk of the data that will disappear as we gather more observations. After all, the universe is vast, and sometimes patterns emerge purely by chance. But the odds of this particular alignment happening randomly are astronomically low, leading many scientists to suspect there's something deeper at play. Could it be evidence of new physics, a hint that our understanding of the universe's origins is incomplete? Some researchers have proposed that the axis of evil might be a sign of a pre-Big Bang universe, a relic of an earlier cosmic era that left its mark on the CMB. Others suggest it could be tied to the mysterious influence of dark energy or even the multiverse. The debate over the axis of evil is far from settled, and it's a reminder that even our most well-tested theories have gaps. The CMB has been a cornerstone of cosmology for decades, but anomalies like this show that there's still much we don't understand. They're a call to explore further, to push the boundaries of our knowledge and uncover the secrets hidden in the universe's oldest light. And as we grapple with this cosmic riddle, another question looms on the horizon, one that's even more profound. What will happen when the universe reaches its end? That's a mystery that takes us into the realm of cosmic destiny. The fate of the universe is a question that has fascinated humanity for centuries. Will it end in fire, ice, or something even stranger? The answer depends on the interplay between dark energy, gravity, and the fundamental forces that shape the cosmos. One possibility is the Big Freeze, a scenario where the universe continues to expand forever, growing colder and darker until all stars burn out and galaxies drift apart. Another is the Big Crunch, where gravity eventually overcomes dark energy, pulling everything back into a single point, a cosmic reversal of the Big Bang. And then there's the Big Rip, a dramatic end where dark energy grows so powerful that it tears apart galaxies, stars, and even atoms. Each of these scenarios paints a different picture of the universe's ultimate fate, but they all share one thing in common. They're shaped by forces we're still struggling to understand. Dark energy, in particular, holds the key to the universe's destiny. If it continues to dominate, the cosmos will keep expanding, leading to the Big Freeze. But if its behavior changes, if it weakens or strengthens over time, the outcome could be very different. The challenge is that dark energy is so elusive, so difficult to measure, that we can't yet predict how it will evolve. The end of the universe might seem like a distant concern, but it's a reminder of how interconnected everything is. The same forces that shaped the cosmos in its earliest moments will determine its ultimate fate. And as we ponder the universe's destiny, another mystery emerges, one that's closer to home but no less profound. What happens when a star dies, and how do these stellar deaths shape the cosmos? That's a question that takes us into the heart of one of the universe's most dramatic processes. The universe, as vast and enduring as it seems, is not eternal. Like all things, it too has an expiration date, a cosmic finale that scientists have been trying to predict for decades. But how exactly will the universe meet its end? The answer lies in the delicate tug of war between dark energy, gravity, and the fundamental forces that shape the cosmos. Depending on how these forces play out, the universe could face one of three dramatic fates: the Big Freeze, the Big Crunch, or the Big Rip. Each scenario paints a vastly different picture of the cosmos's ultimate destiny, and each raises profound questions about the nature of existence itself. Let's start with the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to dominate, causing the universe to expand at an ever-accelerating rate. Over trillions of years, galaxies will drift farther and farther apart, stars will burn out, and black holes will evaporate. Eventually, the universe will become a cold, dark, and empty void, with no energy left to sustain life or even motion. It's a bleak but plausible outcome, one that aligns with our current understanding of dark energy's relentless push. The Big Freeze isn't just a scientific prediction, it's a philosophical reminder of the impermanence of all things, even the cosmos itself. But what if dark energy isn't as constant as we think? Some theories suggest that its strength could change over time, leading to a very different endgame, the Big Crunch. In this scenario, gravity eventually overcomes dark energy, reversing the expansion and pulling everything back together. Galaxies, stars, and even atoms would collapse into a single, infinitely dense point, a cosmic mirror of the Big Bang. This cyclical view of the universe suggests that endings could also be beginnings, with the potential for a new universe to emerge from the ashes of the old. It's a poetic idea, but one that hinges on dark energy behaving in ways we don't yet fully understand. Then there's the Big Rip, perhaps the most dramatic of the three. In this scenario, dark energy grows stronger over time, eventually overpowering not just gravity but the very forces that hold atoms together. Galaxies will be torn apart first, followed by stars, planets, and eventually molecules and atoms themselves. The universe would end not with a whimper but with a violent, all-encompassing tear. While this outcome is less likely based on current observations, it's a stark reminder of how little we truly know about dark energy and its potential to reshape the cosmos. The fate of the universe isn't just a scientific question, it's a deeply human one. It forces us to confront the impermanence of existence and the limits of our understanding. Will the cosmos end in cold silence, fiery collapse, or violent disintegration? The answer depends on forces we're still struggling to measure, let alone comprehend. But as we ponder the universe's ultimate fate, another question arises, one that challenges the very idea of a single, definitive ending. What if our universe is just one of many, part of a vast multiverse where countless realities coexist? That's a mystery that takes us beyond the boundaries of our own cosmos and into the realm of infinite possibilities. What if our universe isn't the only one? What if, beyond the stars and galaxies we can see, there are countless other universes, each with its own set of physical laws, its own history, and perhaps even its own version of you? This is the mind-bending concept of the multiverse, a theory that suggests our universe is just one bubble in an infinite cosmic foam. It's an idea that stretches the limits of our imagination, but it's also one that's rooted in some of the most advanced areas of physics, from eternal inflation to string theory. And while it might sound like science fiction, the multiverse is a serious scientific hypothesis that could reshape our understanding of reality itself. One of the leading theories supporting the multiverse is eternal inflation. Imagine the early universe as a rapidly expanding balloon, with new regions of space constantly inflating faster than the speed of light. According to this idea, our universe is just one of many bubbles that formed within this endless expansion. Each bubble could have its own unique properties, different constants of nature, different physical laws, even different dimensions. Some might be barren, devoid of life, while others could be teeming with it. Eternal inflation suggests that the multiverse isn't just a collection of universes, it's an ever-growing, infinite tapestry of possibilities. String theory, another cornerstone of modern physics, also points to the multiverse. In this framework, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, and the way they vibrate determines the properties of particles and forces in our universe. But here's the twist: string theory predicts that there are countless ways these strings can vibrate, each corresponding to a different universe with its own set of physical laws. This landscape of possibilities suggests that our universe is just one of many, each occupying a different valley in the vast terrain of string theory. But how could we ever test such an extraordinary idea? That's one of the biggest challenges. The multiverse, by its very nature, exists beyond the reach of our telescopes and particle accelerators. If other universes are out there, they're likely separated from ours by unimaginable distances or even different dimensions. Some scientists have proposed looking for subtle clues in the cosmic microwave background, the afterglow of the Big Bang, that might hint at collisions between our universe and others. Others suggest that the fine-tuning of the constants of nature, which seem so perfectly calibrated for life, could be evidence of a multiverse. After all, if there are infinite universes, it's no surprise that at least one would have the right conditions for life to emerge. The implications of the multiverse are staggering. If true, it would mean that our universe is just one of countless others, each with its own story to tell. It would challenge our understanding of reality, forcing us to rethink what it means to exist. But it would also open up new possibilities, perhaps even the chance to explore other universes if we could ever find a way to bridge the gap. The multiverse isn't just a scientific idea, it's a philosophical one, inviting us to ponder the nature of existence and our place within it. As we wrap up this journey through the universe's greatest mysteries, it's worth reflecting on how far we've come and how much further we have to go. From the invisible grip of dark matter to the mind-bending possibilities of the multiverse, each mystery reminds us that the cosmos is far stranger and more wondrous than we can imagine. These aren't just scientific puzzles, they're invitations to explore, to question, and to dream. And while we may not have all the answers yet, the search itself is what makes the journey so extraordinary. So, as we gaze up at the night sky, let's remember, the universe is full of secrets, and every question we ask brings us one step closer to uncovering them. As we reach the end of our journey through the universe's greatest mysteries, it's worth taking a moment to reflect on what we've uncovered. From the invisible grip of dark matter to the mind-bending possibilities of the multiverse, these 20 unexplained phenomena remind us just how much we still have to learn about the cosmos. Each mystery is a testament to the vastness of the unknown, a challenge to our understanding of reality, and an invitation to explore further. They're not just scientific puzzles, they're the threads that weave together the story of the universe and of our place within it. Think about it. Dark matter and dark energy make up 95% of the universe, yet we can't see or touch them. Black holes, those cosmic enigmas, defy the laws of physics as we know them, while quantum entanglement suggests that particles can communicate instantaneously across vast distances, as if the universe itself is interconnected in ways we can barely comprehend. The Big Bang gave us the universe, but what came before it? And why does the cosmic microwave background, the oldest light in the cosmos, contain strange anomalies that hint at something beyond our current understanding? These questions aren't just academic, they're the keys to unlocking the deepest secrets of existence. What's truly remarkable is how these mysteries inspire us. They push scientists to build better telescopes, design more powerful particle accelerators, and dream up bold new theories. They remind us that curiosity is the engine of progress, and that every question we ask brings us one step closer to understanding the universe. But they also remind us of something even more profound, that the universe is full of wonder and that there's always more to discover. Whether it's the search for extraterrestrial life, the quest to understand consciousness, or the exploration of the multiverse, these mysteries invite us to dream big and think boldly. So, what's next? The journey doesn't end here. Every mystery we've explored today is a doorway to new questions, new discoveries, and new possibilities. And that's the beauty of science. It's a never-ending adventure, one that invites all of us to participate. Whether you're an avid stargazer, a casual observer, or someone who's just starting to explore the wonders of the cosmos, there's a place for you in this grand quest for knowledge. The universe is vast and its secrets are waiting to be uncovered. Before we wrap up, we'd love to hear from you. What mystery fascinates you the most? Do you think we'll ever solve the riddle of dark matter, or will the multiverse remain a tantalizing possibility? Share your thoughts in the comments below. Let's keep the conversation going. And if you enjoyed this journey through the universe's greatest enigmas, don't forget to subscribe and hit the notification bell so you never miss an exploration into the wonders of the cosmos. Together, let's stay curious, keep asking questions, and continue to marvel at the infinite mysteries of the universe. After all, the stars are just the beginning.